Hello, everybody. Welcome back to Spatial Statistics. Today, I want to go over the fundamentals of maps and map making. And if we were a geography class, we might spend a lot more time on this, but we are definitely a statistics class. So this is something I want very badly to cover, but in no way will I be as thorough as what you would get in, say, a geographic information systems specific class. GIS stands for Geographic Information System. So we're going to just kind of give us an overview of maps and map making, specifically in R. I will demonstrate how this is done with a real data set, which will be prevalence of childhood asthma in the city of London. But before we do that, just a very brief overview. By the way, the discussion has been great this week. Keep it up. It was a lot of fun to read. I had a great time responding to all of your questions. So definitely well done on the participation component. So our planet. Well, any spatial location is going to be identified by a longitude and a latitude. And last time I mentioned that although most people say lat-long, latitude and longitude, it is more correct, I think, to think of it as longitude first and latitude second, because longitude is kind of the x coordinate, the left-right coordinate, and latitude is the y coordinate, or the up-down coordinate. The biggest takeaway from this slide, I don't want to double cover material too much, is that distances from latitudes and longitudes can be kind of tough to conceptualize, because as we go up towards the poles, either north or south, I suppose we don't want to be biased towards the northern hemisphere, as we go either up towards the northern pole or the southern pole, the longitudes converge. They get close together. Whereas the degrees of latitude are always about 111 kilometers apart. So when you're dealing with, say, 1 decimal degree of distance, that will mean different things in terms of kilometers, whether you are around the equator, whether you are in the North American latitudes, or you are up here in Greenland, northern Canada, or down in around Patagonia in South America, or New Zealand, say. So a lot of times, if getting precise distances is important, which is often, we're going to convert our lat-long coordinates into something called northing and easting. Northing and easting, formally, is the distance between your point and some reference longitude and reference latitude. A lot of this stuff is done using software, but 100 kilometers in distance will mean the same thing no matter where you are. 1 decimal degree of distance will mean different things depending on where you are on the planet. That's the big takeaway. So how does one convert from a 3-dimensional object? I just so happen to have a little cheapo globe. How does one go from a 3-dimensional object like this to a 2-dimensional object as you see on your screen? Well, we need something called map projections. So again, in a geography class, there will be a lot more time spent exactly deriving and describing how these map projections work. On this slide, I decided to just give crash course doesn't even begin to describe it, but basically I am focusing on 4 major projections. These come up again and again, but these are this is by far not an exhaustive list. So we need projections because, of course, we need to go from a 3-dimensional object to a 2-dimensional object that you see on the screen. So first things first, notice that this first image at the top is not projected. If you don't do anything with kind of a map of the United States that's available in R, this is what it would look like. Compared to our first projected map, it's actually using this Lambert equal area. I'm sorry, the Albers equal area. You can see, for example, that the northern border of the US is a straight line in an unprojected sense. But a straight line in 3 dimensions, if we follow a latitude in 3 dimensions, it's actually going to be curved in 2 dimensions. And so using just the first available projection that I have there, you will notice that the northern border of the US is now curved. And at least looking at the US, that's how I can quickly tell whether I'm looking at a projected map or an unprojected map, whether I have a straight line in the north or I have what looks to be a curved line in the north. So that is to say that using any projection is probably better than using no projection at all. So Lambert equal area and Albers equal area, and this is a Albers equal area, I misspoke earlier. It's good for when area matters. When does area matter? When you're mapping aerial data, you will probably be assigning, or you will almost certainly be assigning different colors to different states, counties, census tracts, countries. And so if your Montana, say, is distorted like this, it will take up more of the map. Montana looks almost as big as Texas in this unprojected map. In a projected map, it looks like Texas is a little bit bigger than Montana. And so whatever color is assigned to Texas will dominate that much more than whatever color you've assigned to Montana. The most extreme case of this is the island of Greenland. Greenland, of course, is up here in the north. On some maps, Greenland looks huge, half the size of the US. So if you were going to be assigning a color to Greenland, you really want to make sure that you're using some kind of equal area projection to make sure that the relative abundance, if you will, of certain colors doesn't overshadow the relative abundance of other colors. So over here in the table, we have the distances from the unprojected map compared to distances in our equal area projection. And there are 4 different distances. The ones to focus on are cities that are far apart and cities that are close together. So Atlanta and Knoxville are close together. And in the distorted, unprojected world, the distance between them is 160 kilometers. Once we project our map, either using Albers or Mercator, you can see that there's really not much of a difference. 161, 171, it will not make a huge difference as far as an analysis goes. That is very different than the distance between Atlanta and Seattle. In our unprojected map, Atlanta and Seattle are about 2,000 kilometers apart. I'm sorry, miles. Keep misspeaking today. When we project it using Mercator projection, we get about 50% farther apart. When we project it using Albers, we stay very similar. So the big takeaway is map projections will have a much larger impact on points that are farther apart than points that are close together. And that makes sense because as you go from a 3-dimensional object like this, if you're trying to take a distance between where my fingers are, which is really far apart, and project it into 2-dimensional space, how you do it will affect the result a lot more than where my fingers are now, where basically 2 points close enough in 3-dimensional space, as is intuitive, are almost identical in their relative positions in two-dimensional space. So when you're dealing with a large area, pay attention to map projections a lot more. As far as the 4 projections I have here, we talked about Albers and Lambert as being important where area matters. So when you're working with aerial data analysis, or you're working with point pattern data. In the point pattern data, we will be essentially counting how many points you have per square kilometer, per square mile, per square meter. So to say, to find an average density, for example. So there, how areas in a map are represented will matter. There's a few others. The 2 really common ones, try to erase that. We have Mercator and Lambert. I'd say Mercator is a little bit more common than Lambert, but whenever I say that, know that my lens is statistics and statistics journals. So if that's not the case for your discipline, then forgive me. So Mercator is good for tall and narrow regions. So think of the state of California. State of California is basically mostly oriented north to south and pretty narrow east to west. So Mercator projection has a bunch of what are called UTM zones. And we can just Google UTM zones. For example, for the US, here are the UTM zones. And I'm not coming up with a good picture of it. All right, here are the UTM zones, the Universal Transmercator zones around the world. So if you have an area that fits pretty nicely inside one of these UTM zones, that is longer north to south than it is east to west, the Transmercator, the Mercator projection would be a good one to use. If you're dealing with something the size of the United States is about twice as wide as it is tall, Mercator is not a good option to use. Still better than not projecting it at all, but for wide areas, wide east-west areas, Mercator is not a good option to use. Instead, if you have a wide region, consider using the Lambert projection. So the Lambert projection correctly represents shapes inside of 2 reference latitudes. So you give it basically 2 reference latitudes, and it will represent an area correctly that is inside of those. Something like the United States, something like, I'm thinking of Tennessee, the state of Tennessee, that is a lot wider than it is taller. And finally, just as if all else fails, some of you might be doing research in the Arctic or near the Arctic, but as you start heading, closer and closer to the pole, either the North Pole or the South Pole, both the Mercator and Lambert will fail more often than not. And so for mapping around the poles, the azimuthal projection is used because it correctly works around a given point. So if I flip up to this slide, if you give it the point up here, which is 90 degrees, say latitude, and then use azimuthal projection, it will depict your area around the North Pole or the South Pole correctly. So that's sort of a specialized one that I've only seen a couple of times for very specific areas. So what do we notice around different projections when it comes to distance? Objects that are farther apart, points that are farther apart, are much more affected by your choice of projection than points that are close together. If you're dealing with points inside of, say, a single state or a region of a single state, it probably doesn't matter which projection you choose. And then why are distances important again? Remember that spatial correlation is similar data at similar locations. So distances matter because this gets at the similarity of locations. In addition, if you're using distance as a covariate, say it's a distance from a bad water pump, or it's a distance from a wildfire, or it's a distance from an incinerator, distances will matter a lot then as a quantitative covariate, as will directions, right? So it is worth it to think a little bit about projections, a lot less so if we're dealing with relatively small areas. Okay, let's get to map making. Map making is hard. When you're making a map, you're thinking of what is the major purpose of my map. There's a lot of maps online that look great, but would never really be used in a figure for a journal, for example. One key, I love colorful figures as much as you do. In fact, for the rest of this lecture, I use colorful figures. But in a journal, some of you who have done this, you know that you have to pay extra money to reproduce a figure in color. And so as you're making a map, about 90% of the time, the map that appears in color on your screen will be reproduced in black and white in the journal, at least in print. So don't get too carried away with color. Now, luckily, there's a few definitions about what, if you're using color to denote information, then it's called a Choropleth map. If you're using size, it's called a graduated symbol map. You can combine the two, but my recommendation is don't, because you will lose what I call lazy readers who are just browsing different figures. I have spent countless hours trying to make my own color palettes for maps. I'm a bit of a control freak. I did not want to use defaults. I said, this is my map and I will make my own colors. But really, R has just made it so good and so easy to just use these predetermined palettes that are available through Color Brewer. Some of you may be familiar with it. They're all a product of work of Dr. Cynthia Brewer out of Penn State. She's the chair of geography there. She has done a lot of thinking about color blindness. She has done a lot of thinking about how colored maps transform into black and white maps. My really blunt recommendation is don't waste your time making your own color palette. Although if you do, I'll be impressed. But I don't worry about it. I just use the predetermined ones inside the Color Brewer package. I will show you where that happens in our mapping package. So enough talk, it's time to map. So we will be using TMap. There was a question on the discussion board whether what are some other software packages out there. I mentioned Tableau, I mentioned ggplot2. Off the top of my head, SPplot will do it. There was a few R packages a little bit less known, such as Choropleth. And then of course there is ArcGIS, that is a standalone, expensive GIS software that you can use to make beautiful maps as well. I will be using TMap because it automates a lot of painful tasks, and it has a ggplot2-like syntax, so you can just quickly read what is happening. So I get some kind of a shapefile, which is just a collection of map features. I add a raster to it. So I'm gonna denote elevation by different colors, 10 colors, for example. And then I'm gonna add some borders of the different countries in the world. Here is LWD is line width. And then I'm gonna add some text to the map as well. So it's helpful when you're making these maps, whether it's actually in ArcGIS, a different GIS software, ggplot2, or TMap, to think in terms of layers. And you will see that word appear again and again for the rest of this lecture. Our data set is data I downloaded from the UK National Health Service, which has prevalence of childhood asthma by general practitioner or GP. I have about over 1,200 GPs with their name and their latitude and longitude, as well as easting and northing in meters. So one interesting thing, we're looking at London, England. If I scroll back to this slide and we look at where 0 degrees longitude goes, right? Here is 0 degrees longitude. It actually passes pretty darn close to London. It's actually passing through Greenwich. So that's why when we're dealing with the coordinates of physicians in London, all of these longitudes are very near 0 because we're so close to the prime meridian. We're so close to the prime meridian, or 0 degrees longitude. When we come to meters easting and meters northing, that is again a distance of each GP from a reference longitude and a reference latitude. And you can, that's in meters, right? So you divide by 1,000 to get kilometers. So you can figure out sort of where that reference latitude and longitude are. That's not particularly interesting. In addition, I have a covariate like altitude and meters. Here is my prevalence of childhood asthma. So for example, this GP, Dr. Fateh, had 6.8% of his patients, or their patients, I don't know if it's like a guy or a girl, 6.8% of their patients was diagnosed with childhood asthma. This last variable just converts prevalence into a z-score. So you can see that 6.8% is pretty high when we consider the population of GPs in London. All right. So at this point, I'd like to flip to RStudio, and after I show you how this is done in RStudio, we'll just quickly go through to make sure I covered everything on the slides. So I like to set the working directory. It makes reading in files easier for me. So this is what I do here in this first line. The packages that we need, I need the SF package. Here is my TMAP package. Here is my TMAP tools package. If you don't have these installed, just go ahead and uncomment this line and it will go ahead and install those packages. Just to make sure, I'm gonna run that right there. So the first thing I'm gonna do is I'm gonna download all 4 of London Borough files. So I am be working with a shapefile, and a shapefile comes with at least 4 different files. Only one of them is actually a shapefile. It comes with 3 kind of accompanying files. Whenever you're working with a shapefile, make sure you get all 4. And they're all in this same within the same folder. So on line 11, I'm going to go ahead and grab my shapefile. This is a function out of the SF package for reading shapefiles. Shapefile is very common, and this one was publicly available. If you guys want to play around with this, I have uploaded both the shapefile, the data, and this R code onto Wild Courses. So now I have uploaded something called London Borders, which is the borders of the boroughs in London. If I run this class statement, it's a SF class object. And if I look at what is inside, it's telling me that I have a multi-polygon object, and that makes sense. If I'm thinking about borders, these borders are going to look like polygons on a map. Each borough has a name: Kingston upon Thames, Croydon, etc. Some kind of code, area in hectares. I believe this is area that is non-land. So there's a major river in London called the Thames. This is a designation whether the borough is a part of inner city or not. And geometry field is super important because that tells R what kind of file we are dealing with. So each polygon has coordinates for R to draw. And these, you will notice, are definitely not latitude and longitude. These are in meters easting and meters northing. Finally, notice that we're dealing with the British National Grid. The British National Grid. And if you're pulling down a shapefile that you download from a public database, the British National Grid is used to convert latitudes and longitudes to eastings and northings inside Great Britain. By the way, Great Britain and the UK pretty broadly is much longer north-south than east to west. This British National Grid is really a flavor of Trans-Mercator. And how would you know this? Well, you can look it up online, or you can run this code right here, which annoyingly, we have to recast our borders object as what is called a spatial object. And then we're getting the projection string. We're reading the projection string of this object. If you look at right there where my cursor is, TMERC stands for Trans-Mercator. Trans-Mercator, flipping back to our lectures. Here is Trans-Mercator. It correctly shows shapes for tall and narrow regions. Tall and narrow region definitely fits the description of Great Britain and the UK. Okay? So, to recap, we have used this stread function to read in our shapefile. This shapefile already comes with coordinates for a bunch of different polygons that will represent the boroughs of London. And the coordinates are in terms of meters easting and meters northing. And they were used, we used the British National Grid to map latitudes and longitudes to meters easting and meters northing. So suppose I just wanted to visualize what I've done so far. If I run just plot of this object, it will give me a lot of things I don't really care about. So it will give me a colorful plot with names. It will give me a colorful plot with unique codes. Here are different areas. So the smaller boroughs have blue. The bigger boroughs have yellow. Percentage of the area that is non-land, the Thames is wider over here. So that's why it's coming up as more of the area of these is made up of non-land. Here are the polygons that represent inner London. Here are the polygons that represent outer London. Point is, you probably didn't care about this. You probably just wanted to view something that looks like where my cursor is right now. Like, what is the general shape of the city of London? So in order to plot that, kind of a simple, let's just take a look at what I'm doing plot, you need to plot what is called the geometry. And if I'm going to point out to you, a spatial object comes along with this geometry variable, and these are polygons. So to plot just the geometry as opposed to all the attributes, you have to run what I have over here in line 20. This will just plot the borders. And now, first of all, it's bigger. Second of all, I don't have information I don't need. Third of all, hey, look, it's London, right? Here is the River Thames, you know, and it gives us an idea about the shape of the area we're dealing with. Roughly circular, maybe elliptical a little bit. So I like to always plot this because maybe I had a bunch of different shape files and I didn't know which one I read in. So definitely double check and make a quick plot like this when you're working with shape files you downloaded from somewhere else. All right. Here is my data set. So I gave a quick preview of this before. So this will contain the prevalence of childhood asthma in different physicians' offices around London, you will notice that this does not have a geometry field. Right now, this is just a data frame. And I can't spell. Right now, this is just a data frame. It does not have a geometry field. I don't have a snazzy plot feature because R does not know what kind of spatial features I have there. So what I need to do is I need to convert it into a spatial data format. I'm going to use this st_as_sf object function, and I will set what the coordinates look like. So I will say that the coordinates are easting in meters and northing in meters. And I will tell R to use the British National Grid as well. Because again, we're thinking about layers. So if I'm going to plot the physician's offices over this map of the boroughs, I better use the same kind of projection. I better use basically the same kind of scale. So right here in line 28, it's very important. I convert my data frame. I tell R where to find the coordinates. I could have told it to use latitude and longitude, but I have easting and northing. If you remember, these London boroughs also were using easting and northing as their coordinates. So to put it on the same scale, I need to also use easting and northing. Okay, enough talking, more doing. Now I again have this SF class object. And if I look at this object, I now have this geometry field. It's telling me that my geometry type is a point, right? Each row in my data set is a different point. If you recall, what I have up on the screen was a multi-polygon geometry type. And here is the variable name called geometry. You will notice that every point has a two-dimensional coordinate in terms of meters. So I'm feeling pretty confident that I can just layer these two on top of each other to make a good-looking map. Again, if I only wanted to plot what I have in terms of the geometry, just make sure that things are kind of rolling along as I'm expecting them to go. Again, I have to read just the geometry field, and this will produce only points. What if I wanted to now add in the polygons? I can go ahead and say add equals true, and it will add our polygons right behind it. So this alone is a map, right? This will tell you where our physicians are in London. This doesn't have labels. It doesn't have things like scale, but this is a map. Is it a particularly useful map? I don't think so. We can do better than this. Let me take this away. Okay. So we're moving on to fancy maps, as I call them, where we actually start to make choropleth maps. Choropleth maps is when the color of either the polygon or the point reflects information about that point. So we were going to assign the prevalence of childhood asthma within each physician, which is represented by the dots, to different colors. And now we're going to think in terms of layers. So I'm going to just start from scratch. On line 42, I'm going to add the first layer, which has the borders, the boroughs of London. I have to get this TM shape function in there. It reads the London borders object, and then what to do with it. I'm going to take the geometry of the London borders object, and I'm going to represent it using borders. So if I run line 42, oh, and I was practicing, did not, you will notice this is now a interactive map, which is cool. That's not what I was going for. So I have to set tmap mode as plot. I was going through this lecture, and the very last slide of this lecture, I demonstrate how to make an interactive map. So I don't want to confuse you with this stuff yet. So we'll go ahead and reset the mode from interactive to just fixed and rerun my code. Go ahead and clear this off. I'm apologizing for this. And now go up here. I'm back to just my very first layer, line 42. I just want my burrow borders. Here's what I have. Very nice. Now, again, you're thinking about layers. On top of this layer, I'm ready to add my GPs, my physician offices locations. So on line 45, I just do exactly the same thing, only I make these borders a little bit wider. And I go back to my shapefile. I go back to, to a different shapefile and represent my GP locations using blue dots. This is lines 45 and 46. Yep, there's that. Kind of an ugly map, and by far not what we're going for, because again, what we're going for is to allow every physician, every dot, to have a different color depending on the prevalence of childhood asthma. So my third layer, it starts out the same. I'm still going to have the borders of the 33 boroughs, but now inside this TM symbols on line 52, I'm going to say color equals and assign a quantitative variable to color. If you're familiar with how ggplot2 works, this is identical to how ggplot2 would work. So instead of all of my points being blue, now the color of my point depends on the prevalence of childhood asthma in 2016 to 2017. The palette comes from R Color Brewer. This is YLORBR, yellow, orange, brown. If you want to learn a little bit more about the Color Brewer package, it is helpful to just Google something like this. And here are the names of all the palettes that are available. These are available by default, and these palettes are good. In fact, this is an even more complete set. So I'm just using the first one, second one. I could have used any of these, but I picked pretty arbitrarily the yellow, orange, brown color palette. N equals 6 tells me I'm going to divide this quantitative variable into 6 intervals. How I'm going to do it, in the slides, I describe several methods of cutting a quantitative variable into some number of discrete intervals. I will be using what is called the Jenks method of doing so. Without getting too far into the weeds, the Jenks method basically maximizes the differences between the highs and the lows on your map. It runs an algorithm minimizing the difference within interval and maximizing the differences between your intervals that you're dividing your quantitative variable into. You can do equal, you can do quantile. There are many different styles out there. One of my favorites is Jenks because it's literally designed to maximize visual differences. Here is the title of my automatic legend. I love automatic legends because those take a very long time to make. So without further ado, here is something that looks closer to what a real map might be. All right, so now we have a legend. Notice I have 6 different points, 6 different intervals that I divided my prevalence into. And now every physician is represented by a different color. So for example, right over here, we have a cluster of physicians who are treating a lot of children with asthma. Right over here, we have maybe a cluster of physicians where we don't have a ton of children with asthma. Now, if we are looking at how much data I have. It's 1,225 physicians. I have 1,225 physicians. I have a lot of overplotting, especially here in the middle of the city where, you can have a multi-story building and you can have physicians, taking up different floors within the same building. So I need to do something about the size of these points. I can also do something about this alpha, which will make the points translucent. So the next bit of code does just that. Notice I have scale equals 1 here. Scale equals 1 just reminds you that these are the default size of the points. Right here on line 62, and I have lost my cursor. I found my cursor. Line 62, this scale is 0.5. So I'm going to take the default and scale it by 50%. Leave alpha, which is the translucency of every point, at 0.8. And now I'm going to also add this legend statement. Physician equals left bottom. That's pretty self-explanatory. I'm going to move the legend to the bottom left. I will add a frame, and I will add a title to my figure. All right, all together, here's what I have. All right. So if I was making a figure for a paper, I would probably quit right here, because this map, I think, tells the user where the areas, where there are the physicians who are treating children with asthma. They tend to be, here on the western side of the city, and really outside of the inner city of London. In London, especially like right over here where there are not a ton of children with asthma, or more precisely, there's not a ton of doctors who are treating children with asthma. This is a pretty wealthy area right over here. Poverty is associated with childhood asthma because, for example, if you have rodents or cockroaches in the home, that is a risk factor due to droppings and cockroach droppings and mouse droppings. Cockroaches also molt, and that is an irritant that serves as a risk factor for the development of asthma. So that might be the reason why we have a cluster of low asthma here, cluster of high asthma here. So in short, I think if I was making a map, I would probably quit right here. I don't, because I want to demonstrate a few more of the features to you, but I think this map sufficiently portrays the data. Also, it is good practice to put the year of the data in case somebody just looks at this map and is comparing this map to the data they have. So this is data as of 2016, 2017. This is not the most recent data file. So the rest, again, to emphasize, are just cosmetic adjustments. If you said, well, I liked the legend on the other side of the map, that's fine. We're all going to make different choices for these cosmetic adjustments. But some stuff like making sure that there's not a ton of overplotting is pretty essential. So there's a few things I'm going to do. For example, I would like to add the designation of inner versus outer London. So you will notice that now I'm adding this fill statement on line 71 that will fill the boroughs themselves, whether or not they're considered as being inner city or outside the inner city in London. The rest I'm keeping the same except for the palette, because if I run the same palette as I had before, yellow, orange, brown, you will notice that the color of my points becomes kind of hard to read because the inner London is portrayed with a yellow color. These points right here become kind of hard to see. So the arbitrary choice that I made was to use the reds palette. And although it will look aggressive, I think it will portray a little bit better the different prevalence around the city of London, while still denoting where inner London is versus outer London. Again, the reds was definitely an arbitrary choice. What's left to do? Well, I call it flair because we're getting into more and more optional elements. I will add a scale bar for scale. Important for geography, less important for statistics, mostly because these figures, when they appear either in a PDF file or in print, get shrunk down to a pretty small, they become quite small to the point where, when I add a scale bar and a compass rose, I'm taking up space that I just don't have. But again, to demonstrate the different features of this R package, I will now add a scale bar on line 90 and a compass rose to indicate where north is. This is just good practice for mapping. Again, not required if you're making a figure for a journal. Often not required. Can't speak for all journals. I've also moved my legend to the outside as well. My legend now appears outside of the main map. Moving right along, sometimes it's helpful, for example, to divide this big map into smaller facets or smaller panels. If you do this manually, it's a big pain. So this package has kind of an automatic way of doing it. Right here on line 105, I'm going to facet my map by what is called STP name. STP name divides London into 5 regions, like northwest, northeast. Let's see what that looks like. Is it necessary here? I don't know, but I'm just showing off everything this wonderful package can do. That would take a very long time to do if you were doing this manually. So here is North Central London, here is Northeast London, Northwest London, so on and so forth. It just plots the GPs in that region of London, and it also adjusts the scale bar. I don't know if you can see, but this is 10 kilometers, and this only goes out to 8 kilometers. So it adjusts the scale bar as well to match each facet. And finally, we can make our whole map interactive. I have to run this tmap mode equals view. You saw me reset it from view to plot. Now I am resetting it from plot to view. And it will tell you tmap mode set to interactive viewing. Rerun a previous version using the yellow, orange, brown palette. And it will take just a tiny bit of time to render. If you have a newer computer, this will take quicker. If you have an older computer, this might take a little bit of time. But now, look at how cool. I can zoom out, and it will show me where my data is on the scale of even something like Western Europe. All right, there's my data set. Even, get Italy, Spain, Portugal in there. I can zoom back in and really start to pursue, I think this is very useful for hypothesis generating purposes. If I go to the OpenStreetMap, for example, one of the things that is apparent is where the various airports are. There are a ton of airports in London. You can imagine that airplanes, especially for London Heathrow Airport, produce a lot of air pollution. Air pollution is a risk factor for asthma, especially childhood asthma, where the lungs are particularly susceptible. I saw here on the west side of the city, we had 2 airports and kind of this cluster of high asthma doctors. As we get farther away from these airports, towards the middle of the city, it looks like the prevalence of asthma decreases. So one hypothesis, just by looking at this interactive map that shows where the airports are, here's another airport, and kind of maybe a greater amount of asthma around this airport. There's even, I think, a city airport in here somewhere, if I remember correctly. Yeah, right there, London City Airport. But there, my hypothesis breaks down a little bit, maybe, because although this airport is right in the middle of the city, I see, maybe closer to the average, kind of average prevalence of asthma. So I would use this kind of interactive mode as a hypothesis generating option, less so than for making figures for a paper. Now, if you have a snazzy personal website that you're trying to, woo employers, then you can even work to embed this kind of map onto a website so that people can play around and be wowed by your sophisticated knowledge of mapping software. Okay. So this concludes, really, this lecture. I want to just go back pretty quickly over these slides to make sure I covered everything. If you go back, I make a lot of these notes and writing, so you have these for reference. And I believe the only questions I had were right over here, which is which region appears like it has the strongest spatial correlation. And some of you brought up that it's kind of silly, or not silly, but it's very imprecise to visually assess spatial correlation. And I promise after this unit, we're going to dive right in. In fact, we're going to dive right in with these exact data. So you will be able to quantify exactly how much spatial correlation is in these data. And I will not spoil, there's some. We're going to quantify it just in a week or so. So I think that it's this Northwest London that has the strongest visual evidence for spatial correlation. For example, here is a cluster of doctors with low prevalence of asthma in their patient population, and here is a cluster of doctors where their patients have a lot of asthma. Remember, similar data at similar locations. I think it's this Northwest London, if I grab my stylus, I think it's this Northwest London that has the most clear evidence of strong spatial correlation. Weakest spatial correlation, I'd say it's Northeast London, because there are a number of doctors with high asthma around doctors with low asthma, and vice versa. Here in the Northwest, there's almost a clear gradient of high asthma to low asthma. So clearly, or not clearly, I think in the Northwest, we have the strongest evidence of spatial correlation, as we're kind of thinking about reading these maps. So the question is, though, if we have really strong evidence of spatial correlation in only one of 5 regions, what do you think this means about modeling asthma across the entire city? So in my answer to your guys' participation this week, I mentioned that we'll be assuming that the nature of our spatial process is the same throughout our area of interest. Here, I divided my area of interest into 5 different subregions. And it looks like at least one of these subregions has far stronger spatial correlation than others. So what this shows us, really, is if we have enough data points and a heterogeneous enough region, it makes spatial modeling really hard, because the assumption that all of these doctors, the nature of spatial correlation is the same across the city of London, it's a little dubious. It might hold within each of these regions, but I would be hard-pressed to assume, after looking at this map, that the nature of spatial correlation for all 1,229 doctors is identical. Okay, With that, I will close this video. Watch out for a Zoom link to our first scheduled synchronous activity. I will also post the activity and the data we'll be working with along with the Zoom link. Thank you very much for your attention. I'm looking forward to seeing all of you, hopefully live, all together on Thursday. So have a great start to your week, and I will see you soon.